chapter 16, which is the citric acid cycle, which is the next biggie. We've already gone over glycolysis and gluconeogenesis, the pentose phosphate pathway, which I shouldn't say it's not a biggie, but we don't put as much emphasis on it. And the carbohydrate metabolism in general, it's associated with glycolysis and gluconeogenesis and how they all feed in. Once again, if I were you, I would know my enzyme families and classes and stuff like that, because just knowing that not only will it help you for tonight's exam, but it helps you throughout the rest of the semester as well. And there are always a few that are historical. Once I'm on the name for their backwards reactions, but there's always a few that are historical, like enolase and aldolase. But otherwise, we have some that are pretty obvious, like hexokinase, which we've seen over and over again, so on and so forth. But this is citric acid cycle. Citric acid cycle is unique so far in what we've seen, and because, let me make sure you can see it, I can see it all at least, is that it's amphibolic, so it has both catabolic and anabolic portions to it. Okay? Which so far, glycolysis, was glycolysis a catabolic or an anabolic process? Catabolic, you broke it down. Gluconeogenesis, is it catabolic or anabolic? Anabolic, you're building it all up, you're adding things together. Well, this one is actually both, and so it's called amphibolic, okay? And so, technically, I really abbreviated that when oversimplified it, that whenever they say catabolism, it's the oxidative breakdown of nutrients. Breakdown of the nutrients, and anabolism is a reductive synthesis in this one. And what was, just to really review all the way back from Gen Chem, what is oxidation? Leo the lion goes grrr kind of thing. Or oil rig, what is oxidation? Losing electrons. So typically, what happens here is that I don't like that. Oh, I like citric acid cycle. I don't like the thickness of that pen. That one's better. Okay. You're losing electrons of whatever the nutrient was, because those electrons, remember what in glycolysis, what received the electrons, what got reduced? That goes on to ultimately will make ATPs, but what was the recipient? The whole purpose of glycolysis was you don't actually make hardly any ATPs directly from glycolysis. It was NADH. Remember, NAD plus becomes NADH. And it's because the reason why it gains the electrons from the nutrients of losing electrons. And that's what happens just in general in catabolism, because we're going to see these electrons will ultimately go on to the electron transport chain and be used to make ATP. Likewise, in anabolism, you have things that whatever you're building gains the electrons from something that gets oxidized. Okay, so that's what they mean by that. This is amphibolic, so it plays a role in both catabolism and anabolism. And then another thing that we've got to keep in mind and to review, where did glycolysis occur? What part of the cell in general did glycolysis occur? Cytosol. Gluconeogenesis occurred. Well, it occurs in, right, but what part of the hepatocyte in particular? And technically, remember, there are certain extents, like glucose 6 phosphatase is also in the kidney and also in the small intestines, but primarily the liver is the biggie. But what part of the cell, the hepatocyte? And so I'm just going to draw, there's our cell. Actually, here, let me just do a bigger one. Why cheat our cell? You're going to see this over and over again. Of course, remember, we have a cell plasma, not a cell wall. I've seen people put some really funky things on there. So we have our cytoplasm. Of course, we also have the nucleus. And this is not drawn to scale. We have our mitochondria. And all the parts of the mitochondria. Right, and so what was
Everybody starts in the cytosol, right? And then goes to the mitochondria into the
And so, let's put in what we do know. We know for sure that glycolysis was here. Okay? And so we know that gluconeogenesis has to end there, and it really depended upon where you start. Remember, it could either go this way for gluconeogenesis, or it could go already starting inside that holy of holies for faith integration. And the holy of holies inside the cell is mitochondria, mitochondrial matrix. I'm just going to call it MM for space. And then, of course, this portion right here would be called the inner membrane, and this portion right here would be the intermembrane space, and of course this would be the outer membrane. Okay, so there are types of pyruvate that occur in the mitochondrial matrix, but there's also pyruvate or pyruvic sources out here as well. But regardless, it does have to travel through the matrix, mitochondrial matrix. Remember, it has to, the review for tonight also is just the fact that what's the one player of gluconeogenesis? It's a major metabolic intermediate for multiple pathways, but it cannot pass through the membranes. It's oxaloacetate, OAA. And so it first has to become malate. Malate can go through and then continue on. Oh, I forgot to write. I probably should use different colors, but that's gluconeogenesis. Oh, I can't spell, but you get the idea. All right. And so now the next question is, where does the citric acid cycle occur? I'll use a different color for it. Okay, but what part of the mitochondria? So, if I want to be very specific, it occurs here. So that's citric acid cycle. Actually, if I'm going to do this really specifically, here, let me redo all that. Because part of it overlaps. That's what I'm trying to say. There's one player that is in the intermembrane space, or associated with the intermembrane. I mean, associated with the intermembrane. All the other portions of it occurs in the mitochondrial matrix. Okay, so if you just had to give one answer, it'd be mitochondria. If you're going to be very specific, because you're going to find out that that part that's right here is actually part of the electron transport chain, and so that's why it can over. Just like we're going to find out there's a part of it that overlaps with gluconeogenesis, and there's a part that overlaps with amino acid oxidation, because it's just all interrelated. It's a nice, socialistic experiment there, I guess. It's all interrelated. All right, so this is just showing the answers to what it was, but we have it where the mitochondria occurs in the matrix. I mean, the citric acid cycle occurs in the matrix. I'm in the mitochondria. I will spit it all out eventually. I like this next little cartoon. I don't think I put it in your handout, just because it is very much an oversimplification. But I like that it shows you like the big scheme of things, like what the whole purpose is overall. This was taken from the touchy-feely book that we used to use, which is usually more for, it's a one-semester biochemistry course. It's probably more for like nurses and nurses' aides and things like that. But it does show you the fact, before we were talking about glycolysis, and it's giving off electrons. And the same thing we're going to find out happens with the oxidation of fatty acids and the oxidation of amino acids. They give off these electrons in the form of NADH, FADH2. Citric acid cycle also will give off electrons in the form of one of these, actually in more than one of these, and then these ultimately go to electron transport chain to ultimately make ATP. Okay, and so the purgatory or whatever, the part that connects the pyruvate to the citric acid cycle, we're going to find out is acetyl-CoA. Okay, because pyruvate, I always use Moses in the Holy Land as another faith integration, where it can see, everything that's going on, but it can't enter in directly. And so it first gets transformed into acetyl-CoA. And one time I even came up with like a little devotion. I tried to, and it didn't pan out very well, so I won't try to do it again. But I'm sure you can come up with your own devotion about how you got to be transformed and to go on. But then I forgot. Someone asked me a question about how does, so in that analogy, what would, citrate be? It's like, you're losing it. So I just won't try. So, all right. And this is the exact same thing. It's just, this is the one from your book. One's vertical, one's horizontal. But it's the same type of thing that we can see. We have these the common goal here is really to make these electron carriers, because all of these biomolecules here have electron potential, you know, and so that's the whole purpose of us breaking them down, is in order to get the electrons ultimately to the electron transport chain in order to make, whoops, sorry, I went the wrong direction, to make ATP from ADP. Because as you know, ATP is higher in energy than ADP. All right, so this is it. Don't try to memorize it right here before we go on. That's the big scheme of things. By the way, I usually say citric acid cycle or the CAC. It's also got a couple other names. What's one of the names for the citric acid cycle? Krebs cycle, and by the way, it used to be it's part of what's called the Krebs bicycle. I don't know why it's called bicycle, not bicycle. Bicycle. But it's because it's actually connected to another. Like I said, they're all interconnected. And so once in a while you hear about the Krebs bicycle in TCA. I gave away the other one. Citric acid cycle is one of the Krebs cycle. And the third one's called many times called the TCA, or tricarboxylic acid cycle. Tricarboxylic acid cycle. And so CAC, TCA, and Krebs all mean the same thing. All right. This is what I lovingly refer to as step 0. Some books put it actually as a part of the citric acid cycle. Many do not. It's because, once again, pyruvate cannot enter directly in. And so this step has to occur before the actual cyclic part of the citric acid cycle can occur. This is why a lot of times I call it step 0. Some books won't even show it as part of the circle. Okay, because in reality, if you were drawing it, it would look something like, it would be up here. Whereas this would be the part of the citric acid cycle. It's called oxidative decarboxylation, which is a mouthful.
So pyruvate can't enter the mitochondria at all?
No, pyruvate's in the mitochondria. It can't enter into, I said it can't enter the mitochondria. It can't enter into the citric acid cycle. I'm sorry. No, there's pyruvate in there.
Okay.
Remember, pyruvate can. That's why it's called the pyruvate malate shuttle. I'm sorry, I misspoke there. Okay. So this is the overall, whoops, wrong slide. Scheme. We have pyruvate, which, like I said, if you don't already know it, you're going to know its structure. If you can draw alanine, you can convert it into pyruvate really easily. But this is pyruvate. This is coenzyme A, which is just abbreviated. Remember, coenzyme A is huge, and then it has this little tiny thiol at the end. And so that's why a lot of times they even just abbreviate as CoAsh. It does take an NAD+. In the end, you get acetyl-CoA. You release that terminal carbon dioxide. The carboxylate becomes carbon dioxide, and you get an NADH. And what you're going to find out is in chapter 20 is that each one of these NADHs goes on to make 2.5 ATPs. So ATP is not directly made in this step, but it's made indirectly. And I already pointed that out. Remember, we made 2 NADHs in glycolysis. And so each one of those indirectly will go on to make 2.5 ATPs as well. So that's why you could get total of 5 indirectly from glycolysis and 2 directly from glycolysis. So what class or classes of enzymes could this be? What are some of the possibilities? This is a dehydrogenase, and this one is a dehydrogenase. What was the big reveal? Yes. Okay. It is it does have a decarboxylase activity to it, but it is a dehydrogenase. And so if you want to name this one, what would you name it? Is pyruvate dehydrogenase, and technically, if you notice, it's called pyruvate dehydrogenase complex because it is huge. To put a presence, huge. Okay. All right. And so this is what I mean by it. This is very much an oversimplification. Like, this is the one that came from the Touchy Feely book. They make it look nice and pretty. And it still is pretty, but it's just a more complex beauty than what this looks. Right, you know, the pyruvate, you get acetyl-CoA, kicks off that, and you know, you get your NADH. This is everything that's involved. Yeah. Okay, and you're going to see something like this later on. So this is something that you need to know. Okay, I don't have you memorize every single specific enzyme name. So like pyruvate dehydrogenase complex, there are 3 enzymes. They have multiple enzymatic activities, and so each one of them has like a very specific name based off of its activity. That's why we just call it the pyruvate dehydrogenase complex.
So we won't have to know like the individual.
Yeah, you're going to need to know all the cofactors. Okay, so 2 of them we've already covered. You know, coenzyme A technically isn't a cofactor. I mean, it is coenzyme here, but it's part of the product because that's what ultimately makes the CoA of acetyl-CoA. NAD plus becomes NADH. But then we've got 3 more players. We have TPP, which we have seen in chapter 14. Part 1, by the way. And we have lipoate, which is also lipoic acid. It's just the carboxylate form of lipoic acid, which hopefully, I mean, I don't know if you remember that from like anatomy and physiology days, or if you go over, but it's something that it's a nutrient that you need, and this is one of the reasons why you need it. And then we have FAD, which we have seen FAD. Is if you notice, FAD does not become, or I should say, FAD does not remain as FADH2. Okay? Because we're ultimately going to get an ADH. All right, so we're going to actually break this down even further. So there are 5 players, if you want to think of that. Coenzyme A, NAD, NADH, and then these 3 newbies. Oh, why is it gone? Why, huh? Not for sure why it's off center, but that's okay. So we've seen that stood for thiamine pyrophosphate. Does anyone remember, perhaps it's a good review for tonight, what kind of reactions is it involved in? What does TPP do or help do? And it's one of the reasons why you need thiamine in your diet, which is some of your B vitamins. Anyone want to venture a guess? Like, what kind of thing is happening here, just in general? If we just look here, what are some of the things that we could be doing? What are some of the things that we could be doing that's occurring? CO2 is having to come off. Okay. What else is going? What? I think someone said it. Yes. And so what kind of compound is that coenzyme A that's being, not in coenzyme A, but what kind of compound is being attached to the coenzyme A? What is this? Acetyl. And so in general, what we've seen is this helps activate or move acetyl or acyl groups. We'll find out it also helps with acyl groups, just in generically. Okay? So it helps activate it. It helps aid in that process of moving an acyl group, which remember, acetyl is just a very specific type of acyl group. It's one that only has a total of 2 carbons. Acyl groups from one location to another location. Some of the other, actually we've already seen this. This is coenzyme A, and I've mentioned it before. It's huge. And so I think when I took biochemistry 1, we had to be able to draw all these. I would never ask you to draw all of this. That's just ridiculous. But the important thing here, because you can see all the different parts to coenzyme A, this is one of the reasons why you have to have pantothenic acid, so you can have it, it uses a ribose. It has adenine on it. That's the A part of coenzyme A. But this is the business end. That's what my old professor used to call it. And so I do expect you to know this. So that's the reason why we call all of this part here CoA. And many times we even abbreviate it as either SH-CoA or CoAsh. Because it's the thiol that's really important. That does the chemistry. And then this is when it's acetylated. And once again, you can have acyl groups, like really long carbon groups hanging off of that too. We'll see that with fatty acids, like transferring fatty acyl groups from one place to another. But this is just to show you as an acetyl group. So this shouldn't be anything new. We covered this, I think, briefly last semester, and then also a little bit earlier in chapter 13-ish. Okay. Oops. Here's a new one. I don't believe that we covered lipoic acid. And lipoic acid versus lipoate, I'm going to use it interchangeably. I think most people do. This is when it's oxidized. It has reactive sulfurs as well, but it's either going to be two thiols or a disulfide, an intramolecular disulfide. Okay, so this is when it's oxidized, this is when it's reduced, and it too helps with transferring acyl groups. And so here we're transferring the acyl groups because when it's oxidized, it can't do the attacking. When it's reduced, it can go out and, this is a nucleophile, so it can come and smack that carbon to be able to have it attached to it, and then it can also be smacked in order to have the carbon be transferred from one place to the other.
Could it be acetylated more than once because of the other?
It may be possible in vitro. When you see how the reaction occurs in a moment, it doesn't do that in vivo. I don't know in vitro, at least in theory, I think you would be able to, but... Okay, so this is how the complex comes together. This is a beautiful thing. It's much more complicated than that one that I showed you before that came from the old book. But whenever you see this, and this is the reason why I said I don't make you memorize like dihydrolipoyl transacetylase. I mean, that should make sense, like what it does. But we call it the pyruvate dehydrogenase complex. It does substrate shuttling, and one cool thing here is the substrate never leaves. It's like a little factory. The pyruvate comes in and gets moved along, and then gets kicked out as acetyl-CoA. It's a little assembly line. And these are huge. Okay, I'll show you a picture in just a moment. To me, they remind me of honeycomb cereal, but usually it's because also I really liked that kind of cereal as a kid. I can't eat it anymore, but maybe I'm just hungry. But you'll see the reason why. These are really, really big complexes. But if I'm going to take it step by step, what happens here is we've got a pyruvate that first gets decarboxylated, which we've seen that kind of thing before. We have this whole alpha keto acid and how you can remove this carboxylic acid group pretty easily from it. It's the TPP. And here, if you remember, the way that TPP does it is it has it in this form right there, they call it hydroxyethyl. So see, it's got a hydroxyethyl group on it. And then what happens is now the oxidized form of lipoic acid. Lipoic acid, that long arm of it is stuck to a lysine. And that lysine literally does flip back and forth, like what we've seen before with TPP and some of these. Because it's flexible. It's got a long, 4 carbons down, and then it can move around. And so what it does is it takes the hydroxymethyl group as an acetyl. So now that's why it's called now acyl lipoyl lysine. And so the reason why is because it's a lysine. It's got a lipoic acid. And if you remember from the naming from organic chemistry, just to review, when you named carboxylic acids, you can drop the ic acid and you add YL. That's one of the reasons why I had you. So it sounds funny, lipoyl, but that's what it is. So it literally tells you what it is. Then what happens in the second big enzyme subunit as well is coenzyme A itself comes in and just literally smacks this carbon. You make your tetrahedral intermediate, you get collapse. So that way you get the reduced lipoyl lysine, the reduced lipoic acid on there, and you have your product. But notice, we don't have any way first of all, we haven't made the NADH. And secondly, we've got to get it back to the oxidized form in order for this to go on, otherwise we'd short circuit. And so what happens here is an FAD comes, and the FAD comes and it gets reduced. So it oxidizes the lipoic acid. So you go from FAD to FADH2. And then as a final step, the NAD plus comes and it takes those two hydrogens and the two electrons to make NADH. So that's why this first one technically is the pyruvate dehydrogenase portion. This is called the dihydrolipoyl transacetylase because it's moving the acetyl group from one location to the other. And then finally we have the dihydrolipoyl dehydrogenase, but they call the entire thing the pyruvate dehydrogenase complex. Because I mean, it's huge. But this is how we get the NADH.
So the lipoyl lysine, the disulfur bond that's there gets broken down by the hydroxyethyl TPP?
Right, the TPP, this breaks this apart. Because then if you do, if you've set and you figured up the oxidation state, see this is oxidized, this is reduced. Remember, because this has more carbon-oxygen bonds, this has more carbon to hydrogen bonds than only a single bond. And those electrons got passed off to this to break it apart. And I just don't show you the electron pushing is more complicated than that. But, there are people that really look into that looks in the electrochemistry and biochemistry of it. Because if things go wrong here, obviously, then it throws the entire scheme off. Same thing here. The electron shuttling between FAD and NADH is a little bit more complex because they can. What you'll find out is they can even form like what's called semiquinones, where they can pass them off one at a time.
So where's the coash coming from?
The what?
The coash?
That's the substrate. So yeah, you have acetyl-CoA, and we're going to find out that one of the major places that we get acetyl-CoA is from the breakdown of fats or fatty acids. Okay. This is what it looks like. I told you it's huge, and remember, it had an E1, E2, E3, so that'd be 1, but it comes in with multiple pyruvate dehydrogenase complexes to form the big honeycomb-looking thing. And so, I mean, it is a massive. You can even see it in microscopy. See? And so that's why, I mean, yeah, approximately 50 nanometers across. I mean, that's big whenever you think about it in the big scheme of things. All right. So we're going to actually move on to the citric acid cycle. So we did step 0. We got an NADH out of it, and we transformed, be transformed by the renewing of your mind. Ah! Okay, phase integration. The only thing it had in common was transform. Sorry. It's a push. Okay, so we have step 1. Remember, this is a cyclic thing. So just to review, we had glycolysis, we had gluconeogenesis. Both of those, were linear. That's an oversimplification. Then we had, what would be pyruvate going to acetyl-CoA. And then we have, you can't see it, but down there, it becomes the citric acid cycle because it's cyclic. Okay. This is step 1. So we have so this is the acetyl-CoA that came from the pyruvate, and it hooks up with oxaloacetate, which is OAA, which where have we seen OAA before? Gluconeogenesis. So we already see, here's one. That's why that one little picture I did at the very, very beginning, I showed how the citric acid cycle kind of touched. That sounds sick. Intersected, especially, yeah, okay. Intersected with the gluconeogenesis, and it's through OAA. So, under times when you got lots of energy, OAA is going to go towards gluconeogenesis, right? Because you want to store it. In times when you need energy, the OAA can go towards citric acid cycle because you need to make energy. Oh, whoops, I went too far. All right. So, yes. We have OAA, acetyl CoA. There is water. It's a hydration reaction or condensation reaction, I should say. And you make citrate in coenzyme A. You got your coenzyme A back, so that way it can go back up to do. We're going to find out coenzyme A is involved in lots of things, but it could go back into this instance, go back up to the pyruvate dehydrogenase complex. It's a mouthful. In order for the reaction to continue, the cycle to continue. This is one of the reasons why it's called the tricarboxylic acid, because if you look, 1, 2, 3 carboxylic acids. So that's why it's also called the TCA. It's also called the citric acid cycle because citrate. In vivo, I don't know why we call it citric acid cycle and tricarboxylic acid. In vivo, they've lost their hydrogen, so they are the 8 forms. It's just carryover, I guess. Okay. So what class or classes of enzymes could this be? Maybe a carboxylase. What else could it possibly be? Because what are we actually making right here? Or, I mean, what kind of reaction is undergoing? You are transferring...
The OH?
But are we getting rid of the carboxyl group on the acetyl-CoA?
Well, I mean, you're getting... No, you're not getting rid of it as a carboxyl group. You're getting rid of it as a thiol, right?
But you're breaking down that double bond of oxygen. Oxaloacetate, right?
Oh, you are. That is true. You are breaking all this down. What else could this be? What are some other classes of enzymes? We said carboxylase. You could say maybe a hydratase, I guess, if it was named for the backwards reaction for getting rid of water. What else are we doing? Just in general. I mean, sometimes think about really simple things. How many carbons are here? 4. How many carbons are there? 2. How many carbons are overall? 6. So 4 plus 2 is 6. So what did we do here? We're not just transferring. Like if you're thinking about, I don't want to say because I'm going to give away. Like if this was the elementary school and we got 4 blocks and we got 2 blocks and we put them together and we got 6 blocks. Like we're building. So if we're building something, what kind of enzymes can? So we have synthases and we have synthetases. And so what one could this one be? So what were the differences?
Without using ATP, it would be synthase.
This is a synthase. So this one is, if you want to name it, it would be called, this is synthase. See? We just haven't really worked with synthases yet. But that's why it makes sense. We have something 4, we have something 2, we're building together, we're synthesizing. We're synthesizing. There's no ATP that's utilized or GTP that's utilized here, so it's going to be a synthase versus a synthetase. And now we're going to find out that what would be some of the things that would make sense to inhibit. It's allosteric. What would be one thing? First of all, in general, are you going to inhibit this when energy is high or when energy is low? High, right? Because this is to make energy. So citric acid cycles to help you make energy. So what's one indicator that we've seen that is something that shows, okay, we have lots of energy? ATP. That's supposed to be a T. All right. Does anyone remember, what was another one that we've seen? Another small molecule. You've got lots of it around. If you've got, it's Na, which one? NADH. Okay. Then we have a new one, which I would give almost a bonus point on the hand if you knew that one off the top of your head, because it's the newie. And it won't make sense at this point in time, but it's succinyl-CoA. And the reason why is succinyl-CoA is one of the intermediates further down in the citric acid cycle. We just haven't seen it yet.
SUCCIN.
Yeah, here, wait a minute, in case you can read my handwriting. It's further down. And please don't just memorize, the steps and say, okay, step 1, citric synthase, because First of all, what I've been known to do in the past is I orient it differently to where step 1 won't be at the top of the page. And I've been amazed at people that still go in order because they just memorize 1, 2, 3, 4. But yeah, you know, it's a circle. There is no top or bottom. Like, how do you know where the top or the bottom is for this ring? You don't know. You know. So on mine, obviously it was a wedding ring for a girl, maybe you can do that. But okay, so that's why I just understand the logic behind it. This is just a picture depicting everything. It's really, I mean, I find it really cool in the sense that, you know, you can see it's a dimer. You can see how we've got acetyl-CoA. Well, this is an analog for them to be able to crystallize it, but something that looks an awful lot like acetyl-CoA, that's oxaloacetate. They come in together. You know, they get smushed up in order, which I just spit all over this iPad. You get smushed up together to ultimately make citrate.
So is that supposed to be like 2 of them? Is this like...
Yeah, this is a bimodal, like bifunctional, which you see a lot of times. You've seen dimers and things like that. Mm-hmm. All right, so now we're ready for step 2. Oh, I forgot. I should have looked ahead. I do this every single year. Every year. I've got a t-shirt for this. And every year I'm telling myself, you know, I'm going to wear my t-shirt. I'm going to wear my t-shirt. I have never, ever worn the t-shirt on the day that I do this. Once again, I forgot once again. All right. What? I'll try to remember. It's kind of hard, but yeah, yes. Gotta what?
Something about a Ferris wheel.
It's a Ferris wheel. Yes. Like you just got to. All right. All right. So step 2, actually, whoops. It's a dehydration and rehydration. The final product is called isocitrate, because all you did, if you notice, is you just move. It's an isomer of citrate. Okay. And so you moved what apparently the alcohol from being the middle carbon to second carbon. And one other thing just to point out is, which is different if you think back to organic chemistry, remember you couldn't take something that was achiral and turn it into something that was chiral unless it was in a chiral environment. Like it's just not possible in vitro. But our body does it in vivo because the enzyme itself is a chiral environment. So we took something, this is achiral, because you can see the top, quote unquote, top and bottom here are identical. So that one's achiral, but now it's chiral. In fact, we have 2 chiral carbons. Okay. It has an intermediate, but the intermediate doesn't leave. Okay. The intermediate's called aconitate. And this one, and I didn't hide this, but this one actually has a different cofactor than what we've seen in the past. You know, we've seen magnesium before. This one requires iron. And they call it the Ferris wheel, which I don't know that I actually put the... Oh, I did. I put a little bit in there. Yep. Because what happens is the whole fact that the iron changes its oxidation states, and you get the ferrous ion back. Does anyone, I'll tell you right now, this one has its own name. It's like we have enolase and aldolase. This one has its own name, and this one, unless it's something that you are well studied on. What? It's aconitase. It, for whatever reason, historically, I don't know why, but it's named for the intermediate that's formed. It's aconitase. Here, I'll do it on the next slide. You can see it. It's aconitase. This is the historical side effect. Some figures, I don't remember if the figure in your book does it or not, it actually shows, it kind of throws people off. They just memorize the names and like the order, like steps 1 through 8. There are 8 steps, by the way, if I tell you that. Not including step 0, there are 8 steps. And the reason why is because they show it as 2 distinct halves. And so like step 2A is step 2B. And so if you just sit there and memorize, like, okay, these 8 names in order, you won't figure it out. Okay, you'll come up one short. And so it's because aconitase transforms it from citrate to aconitate, and aconitate to isocitrate. So this is, and we're going to see this kind of thing later on. It has what's called an iron sulfur center. And this iron sulfur center is required for both binding and catalysis. And there are different types. And unfortunately, at least whenever I taught, even when I taught Gen Chem, and I'm pretty sure also when Dr. B taught Gen Chem, we just don't have a lot of time to go over inorganic chemistry. Some of this you pick up along the way, like zinc, for example. I know at least in chemistry and cancer, we talk about how zinc is special because it only has one shape, it's tetrahedral. But there are certain other transition elements, in particular metals, that can have multiple different. That's so bad. That's horrible speaking. You can have various shapes, and it can change from one shape coordinating to another shape and things like that. Well, iron can do that, and based off of what iron is attached to and the shape around iron, it changes its reactivity, okay? And so it changes whether or not it's Fe2 plus or, Fe3 plus and all this kind of stuff. And so we see these different iron sulfur clusters doing lots of electron transport chain kind of thing, like electron transports, and we'll find it a lot in the electron transport chain. And sometimes it's just an FES. This one is what, 1, 2, 3, 4, Fe4, 1, 2, 3, 4. Yeah, Fe4, S4. But we see here, this is octahedral. See, it's got 1, 2, 3, 4, 5, 6. It's an octahedral. It makes an octahedron. Whereas this one over here is tetrahedral, and it's just to show you the complexity. But please notice what kind of amino acids are used, or functional groups that are used to, it's called coordinating to the iron. And usually we're talking about cysteines. Okay, now you can have, this is citrate. You could have something like an aspartate or something like that, right? Because it's got oxygens on it. Once in a while you can see a nitrogen that can do it, but usually we're talking about sulfur and oxygen. Especially here, we're talking about cysteines, since it's part of an iron sulfur center. And I would never ask you to show how the electrons get I would have to look that up, and I couldn't even guarantee you that I would recognize or understand all the electron pushing involved for that one.
You said that iron there was...
This one?
Yes, you said it was
It's called octahedral whenever it's got 6 things.
So do we just assume that the other 2 bonds are hydrogens?
The other 2 bonds, see here. No, octahedral means, it makes an octahedron. Let's see, which, I can't draw it. Let's see. Let me see if I can draw it. An octahedron looks like this. Okay, and then whatever's in the middle is coordinating to like 2 pyramids on top of each other, right? Because there's 1, 2, 3, 4, 5, 6. It's whenever there are 6 things. If you think way back to Gen Chem, I don't know why. See, because there's 1, 2, 3, 4, 5. There's only 6 sides. I don't know why they call it octahedron. I don't know why. But yeah, they call it the octahedral. It's an octahedral shape. To me, it just always kind of looks like 2 pyramids on top of each other.
Mm-hmm. Well, do the pyramids per se have 4 faces? Is that why?
Maybe. Maybe, because I don't know the history behind it. Because there's 1, 2, 3, and then the base would be 4, and then the same thing from the up above or whatever. But, or maybe there's 4. No, there's 4 steps. Isn't there? 1, 2, 3, 4. See, that's why I was horrible at geometry. So yeah, that would be the octahedral part. Because I'm only seeing 3, but no, there's the 4th one because it's a 4 base for being square planar, having square planar bottom. Mm-hmm. Yeah, so that'd be the reason why it's called octahedral. No, I did. That was the only math class that I struggled in. What was really bad was my sophomore year in high school, and for the first 2 or 3 weeks, I really, really struggled with it. And it's because I was too embarrassed to let the teacher know that I was colorblind, and she used all these different color talks and stuff. And so once I went to her for help, which is one of the reasons why you should go to your teachers and professors for help, she sat down, we figured out ways, and I actually ended up getting an A in the class. But I had to work really, really, really hard, and I did not like geometry. Okay, and that's why I think, let me see what the next step is. Yeah, we're going to actually stop here at step 3. Okay, so we went over the first 2 steps.